جلستنا هذا اليوم تبدأ ستام والذي سيحدثنا عن تقنيات والمشاكل المصاحبة لرصد الهلال النحيل والرفيع جدا باستخدام التلسكوب. Honorable guests, ladies and gentlemen, in this second session I would like to start it with Stattam, and he will tell us about the telescope and the problem, difficulties, challenges facing observing the thin crescent with the telescopes. Jim, he came with a wide interest in astronomy when he was a teacher, introducing the subject to the student and motivating them, and also his interest in the crescent problem, because he, in his free time, would like to spend it and also to utilize the latest technology, how to trace the moon in different circumstances, in different situations, to see in reality and with practice the possibility to be able to observe the moon or not. So he will, in his very interesting presentation, he will tell us about the challenges and the problem and maybe some solution, how to overcome some of the problems that he faced. So please, Jim.
First, I just want to thank the organizers, the sponsors, everybody else that's worked so hard to produce this.
The mic.
I forget those little details. It'll come on. Okay, thanks. I just wanted to thank the organizers and the sponsors of this conference. It's an important conference. It's unique. And I'm highly honored to be part of it. Back in the 70s, I reacquired a lifelong hobby I had of astronomy. And somewhere along the line, I read about a 15-hour-old moon that was an ancient record and learned that looking for early moons was some kind of an amateur astronomy sport. And I thought, hey, if you know where to look and when to look, there shouldn't be any big deal. Okay, the when is easy. Practically all of the calendars have the new moon icons. The where was a little more difficult. Every point on Earth is different, and every point in time is different. So it's going to take some calculations. And I remember spending like a half a day doing the first set of calculations. And then I had to reserve the other half of the day to find out all the mistakes that I made. And this isn't going to work, you know. So there were these newfangled contraptions called computers then, and I thought, well, I'm going to have a computer. Then, of course, since there's no software yet, I'm going to need to learn programming. And this is kind of a fun aspect of the hobby. But eventually, I was out looking for clear horizons and thin lunar crescents. And I probably went 10 years, and I didn't get anywhere close to the record, which I think at that time was held by Robert Victor at the University of Michigan, 14.3-hour moon. And I thought, well, the best I can do is just a personal best, try to get the smallest and smallest. But I just happened to be lucky enough to be in Tucson, Arizona, when all of the geometry came together, all of the atmospherics came together, and a group of us were able to see a 13.2-hour-old moon. And this is really exciting, and it got me interested, and that's when I first found out that most of the world's population depends on seeing new moons for their calendars. So I thought I'd do some research, and I tried to read up on all the papers I could find. I visited Danyan and looked at his limit. And I came across a lot more questions than answers. You know, how could I tell if these things were correct or not? Some were, but probably some weren't. And did the 7 degrees that Danyan came up with settle things? Well, not necessarily. We'll see that people have done better. And I learned of Dr. Derek McNally, the director of the London College Observatory, who revisited Danyan thinking that he'd made mistakes with his topography of the moon, that he assumed too smooth of a moon, and that there was more to do with atmospherics. And he came up with something less than 7, maybe even 5, and he told me years later that he never received so much vilification in anything that he had ever done than publish that paper that the Danyan limit was less than 7 degrees. A couple of years later, Dr. Bradley Schaefer, now at Louisiana State University, revisited Danyan and came up with a confirmation. Yes, indeed, 7 degrees. So see, there's more questions. And to top it off, a lot of the studies that I read were using empirical evidence, empirical information. The investigator would ask, did you see the moon? And if the person said yes, okay, the moon is visible. Did you see the moon? The question is no, the moon is invisible. And so on. Well, as you all know, that because you don't see it doesn't mean that it's invisible. Now, what do we need to know to go out and look at these things? We need, of course, be aware of the age. We don't want to wait till an obvious moon is there. It's important to find the moon that's close to the Danyan limit. And we need to look at things like contrast that is a result of a dark sky. How does the sky get dark? The sun sets and gives us time to see the moon. Well, we're not going to see the moon unless it's far enough away from the sun, elongation, so that there's a good part of the edge of the moon illuminated. But if the elongation is in a horizontal fashion, we could have the moon set, the sun set a couple minutes later. We don't get anywhere. If we get this kind of a situation where the moon sets and we get enough time, the sun sets, we get enough time for the moon to set, we have a long lag time, the difference between moonset and sunset. And this is what we're looking for. That's what came together in 96 when we saw the 13-2 moon. Now, where do we get all this stuff? Well, there are lots of places, but there's only one place I know of that is precise and comprehensive, and it's only a part of something much, much larger. With just a few clicks of the mouse, I get a printout of everything I need to make a plan. And the plan is essential if you want to look at some of these threshold crescents. Now, remember I mentioned that we had some criteria. These are obvious criteria: the age, the relative altitude, the elongation, and so forth. There are a couple of important criteria that aren't so obvious, and one of these is the position of the moon. Okay, where is the moon? You can't just say, look to the west when you're looking for the thresholds and when you're looking through an instrument. You need to be more precise than that. Now, I looked for the moon a couple weeks ago. I didn't see it. In fact, I didn't really try to see it, but I did take some pictures. I took a whole lot of pictures trying to get a series of slides that I could demonstrate something for you. And this worked out. At least it works out on the computer screen, so I may have to lead you through this a little bit to see if I can make a point. Each slide is twice the zoom or twice the magnification of the previous slide. And there are 4 of them. So we start here with a wide-angle picture. You're going to see a little better than this when you do go out and look to the west. But I think you can all see Venus. Can anybody see the moon? Okay, let's double up. Oh, thank you. And now we're somebody with good eyesight. is looking to the west. Any of you people with good eyesight see the moon yet? Good eyesight? Not yet? Okay, let's double up again. The low power binocular field. Anybody see the moon? We're going to have to double up again. Anybody see the moon? Hey, there's a bunch of people that see something, right? And you're telling the other people where to look. You know, maybe something like twice the elevation of the, or twice the height of the utility pole, a little bit to the right or up, and underneath the cloud. How many see it now? Okay, let me back up a slide. Nobody saw it here. Anybody see it now? A few of you think you see it. I'm going to go forward again. You can see it now. No, it's there. It always was there. This is true through the telescope eyepiece also. How many can see the 13.2-hour-old moon here? When I show this slide, or this is the drawing that I did. When I show this drawing to people, very few people see it unless I point it out. You saw it first. All right. Now, most of you can see it, or some of you anyway. Some of you need to have it focused, right? I told you my voice was going to go. Focus is another important criteria that's quite often overlooked. And it's extremely important because it doesn't matter how precise you are when you're looking for the moon. If you're not focused, you're not going to see it. So I tried to take this diagram and fudge a few pixels to simulate a better focus. I don't know if it's going to work here. But how many see the moon with it pointed? You can see the actual white arc. Not too many, huh? Didn't come out too well. Well, let's see if the focus does anything. It helped for a few people. So there it is. Now, if I back up, and you know where to look, you have a better chance of seeing it. And my newer scope now has this little contraption on it so that when I do finally get a focus, I back off and I remember what it is. Because you're going to get to that point when it's either getting light for an old moon or not getting dark enough for a new moon, where you start thinking, I don't see anything. Maybe it's the focus. And you turn the focus a little bit, and that's it, boy, you've lost it. So it's a good idea to have something like this where you can actually have a number for your focus. And it's also a good idea to have something like this when you have a group and you pre-focus, everybody can get their own number. And you don't find the moon and then tell some guy to take a look, and he spends the whole time that the moon sets trying to focus it, and nobody else gets a shot. Now, this is from my home in Tucson, Arizona, and it's looking east, directly east. And it's where I look for a lot of the old morning moons. Those are easy because you got all those stars that help you out when it's dark. But Brad Schaefer told me after he confirmed Danyang's limit, when I said, ask him if there was any chance of seeing something that was like 6.5 degrees if we went up Mount Lemmon, this mountain in the back, and there's a little white dot there that is an observatory. He said, indeed there was. He did his calculations based on sea level. So there should be an advantage to elevation. So we threw our scopes in the car and went up the mountain. Didn't have much success the first couple of times because we overlooked some things. Let me see if I can kind of point out what we have here. Does this mouse show up on the screen? No, it doesn't. So. Okay. Generally, what you're doing if you're at the surface and you're looking straight up at the zenith, you're looking through an atmosphere. You just arbitrarily give it the one atmosphere. That's also a scientific term. If you're looking along the horizon, you're looking through 3 atmospheres. Quite a handicap. So I've exaggerated some mountains and some distances on this diagram. Tell you what we did the first couple of times. We scampered up this mountain and we're jumping up and down. We're so happy now. We can see a moon that's like 2 or 3 degrees below the zero horizon. We're going to see it for 10 or 15 minutes longer than we would back down in the valley. And it didn't work. Well, one reason is, of course, the sun was 10 or 15 minutes too, so we don't get any advantage in the lag. But another reason it doesn't work is because when you're up in that mountain and you're looking down, let's say, past where I live, and you're looking at the tangent, well, you've got 3 atmospheres here plus a little bit more. So where's the advantage of going up a mountain? Not in this situation. And if you were to look straight out, you can get less atmospheres, but remember, the moon is going to be higher. It's going to be 4 degrees up. The sun's going to be correspondingly higher, too. So just the top of a mountain looking at horizon phenomena isn't a big help. This is a situation where I'm looking up over the moon and I'm seeing through less than 3 atmospheres, but I'm told that there's a lot of scatter all through here, and that's light scatter is going to decrease the contrast more than any advantage I'm going to get from looking through less atmosphere. I'm not completely convinced, although I don't know anything about that. So I keep looking from my home across here. And, now, the situation that does work is you go up the mountain, and if there's another mountain, 50 kilometers, 100 kilometers away, you can look at that zero and get less than 3 atmospheres. And that can all be filled in between the mountains, too. And so there is the advantage here if you avoid that, looking down, thinking you've got some extra time. Now, we're armed with all this information now. We know the criteria, the obvious, the important but not so obvious. And we take our instruments wherever we think we're going to have the best shot. And the first thing you need to do for looking at a morning crescent is to align your instrument, calibrate the setting circles. And you do need some measurements. These go-to scopes just aren't precise enough. And in the dark, you can see the North Star, so you can polar align. Ironically, it's not so important to be aligned in the morning because you're going to pre-focus or preset your scope. But once you do that, and I'm going to run through the rest of these real quickly here so I don't run out of time first. You take your scope and you go up somewhere where you can see a predetermined field of stars through your eyepiece. And this should be on the same declination that the moon is going to be on. That way you can slew your scope back down the horizon and you're on the same declination. You can draw another diagram of stars. You can do this several times. And then as the stars rise with the moon somewhere behind there, you can be pretty much on the right location and the right declination. And then if you know what stars you're looking at and you know where the moon is supposed to be, you can calculate how much time it's going to take for the moon to get to where you need to be. Now, this is the second sheet, besides all that information from Accurate Times. And all of these little diagrams I've been talking about, all this pre-stuff that's in there, the pre-calculated and predetermined, is all written down here in your second observing sheet. And then I use one of the planetarium software applications. There are lots of them out there. I like Starry Night Pro. And I've done one of the features it has is you can do a QuickTime movie of what's happening in Starry Night Pro. So I'll go and I'll preview this whole observing thing. That's where I get the diagrams and things. Let's see if I remember how to do this. No, I didn't. Okay, here's what we're looking for. An old moon rising with a thin crescent. And if we know where to put the scope, we've got our finder outline, field of view, and the eyepiece outline. And we're running things backwards. Notice they set. This is in the morning. So we're running all of the stars and things backwards. When we get to a bright star that goes through the eyepiece field, I'll zoom in there and then I'll diagram that on my observing form. And I'll choose 3 or 4 of those, sometimes more, because it's kind of fun just to watch them go through and see how you predicted something. But remember, you're tweaking the scope each time, making sure that your position is more and more precise and the focus. This may be the last one when you're high enough in the sky. This is the first thing I'm going to go to. So I put the scope there, knowing that if I've aligned it correctly, I'll be back to where the moon's coming in. And then we slew back down to the horizon, watch these predetermined star fields go through, time them, know what time the moon is supposed to be there. Use your stopwatch, your radio, whatever, and watch the star fields go through there, tweaking all the time. And then it starts getting bright on you, and you start losing stars, and then you got this big, long stretch of time where you're going, oh, man, I hope I didn't do something wrong. No, it's got to be there. The only thing that could go wrong now is if clouds came in or something. And your watch will tell you, or your radio will tell you when the right time is there, and that's when you engage the clock drive and follow the moon up. If you don't see it now, maybe you'll see it a little bit. Or maybe you won't see it, which, darn, that's why I get so many negative observations. Okay, now the more practical application is to find the new moon, the evening crescent, the pertinent moon. It's a lot harder, though, than it is for that old moon when you have the dark sky. And you have to, first of all, put your scope out there and polar align it, because this is more critical also. Now, how do you do that in the daytime? Unless you have a permanent mount or you've done something the night before. But quite often I'm dragging the scope somewhere and I have to set it up. So when my original scope that I used for 20, 30 years fell off the mount and shattered the lens, I bought one with a lot of neat attachments. The first one was a latitude adjustment scale. I set the latitude just exactly where it should be, and then I have one of my 2 axes taken care of, as long as I can level the scope. And when it's level, the latitude is set, I'm pointed towards celestial. At least I have the altitude of celestial north. I've used a compass to try to get to as close to true north, but how do you get that final critical distance? This knob on the right actually turns the mount in azimuth. So you need to turn it. Now, how do you know how much to turn it? Well, you take something like the sun, which is still up, and you point your telescope at the declination of the sun on your declination setting circle. And if you do that precisely enough, you turn that knob that was on the right, left or right, until you bring the sun centered on your declination line in the finder scope. And now you are precisely polar aligned, and you can put in all of that information, all those pre's in your observing form. You'll need to know, where these things are and how long it's going to take to get from one to the other and so on. Calibrate your setting circles and so on. Starry Night showed me what the situation 2 weeks from now will be at my home. And the moon is only 7 degrees from the sun. And this is cool. I get to break Danyan's record again. So you slew to a bright star, a little more focusing. Well, I've got Venus here at the top. And that's pretty bright. And if I have enough time, I'll go around to all these other stars. They're all visible if you point the scope at them. And if you're really lucky, there'll be a star right where the moon, at least at the altitude, the moon will be when you hope to see it. And that's, well, in this case, Sirius is going to be down there. You can't get more lucky than that, can you? And that's going to be your focus. That'll be just exactly where it needs to be. And it does change with the altitudes and the temperature and I think the brightness and a lot of other things that I don't understand. If you don't have a Mercury or Venus or something in between the sun and the moon, you'll have to go on the sun and then offset from the sun and wait for the moon to come into position. And use the same kinds of things that you used for the morning moon calculations and measurements. You see that the moon isn't following the sun exactly. It's a little bit offset, so you've got to move your scope. Well, first the thing, I'm getting ahead of myself. First, you point on the sun. You know how long it's going to take to get from that right ascension to the moon's right ascension. So you disengage the clock drive and start your stopwatch. And then while you're waiting for the moon to come down, now you move the scope either north or south of the sun precisely how far you need to move it to take care of the difference in declination between the sun and the moon. My declination knob, one turn equals 6.89 arc minutes. So you can be pretty precise after you do a few of those. And here you have the eyepiece field offset a degree or so from the sun. And you're timing it. And then you watch the sunset. And it starts getting darker, and you hope it gets darker and darker. And you keep thinking of all the things you did wrong. Oops. Back. The moon gets into the right position that you can only tell by the timing because sometimes you can't see it. Now you engage the clock drive and you follow it for like 2 minutes or less till it sets. Now sometimes you can get 10, 15 minutes and it will get much darker and the moon will just pop out of the field. Well, thanks very much and good luck in your observations.
Okay, many thanks for this very interesting illustration of how observational astronomy can be improved and can be planned to get the very thin crescent.